This video is about the Diffie-Hellman Key Exchange Protocol. This protocol was developed so that if you've got two people trying to communicate with each other securely over a distance, and all they have is an unsecure line between them, they could then use this unsecure line to pass some numbers and create a secret key, which they could then use to encrypt any further messages that they want to send to each other. So if you have an eavesdropper in the middle, such as Eve, she could see all the information that they're passing back and forth between each other and still not know what their secret key is that they're using to encrypt their messages. The Diffie-Hellman Key Exchange uses Modulo Math, so two people can exchange numbers over a non-secure channel, and then they can use these numbers to compute a secret shared key. And that's what makes this kind of communication possible here. The Diffie-Hellman Key Exchange starts with two numbers, G and P. G is just some number and P is a prime number. Now G isn't just some number, it has certain qualities with regard to modulo math, but we're not going to get into that here right now. Just for the time being, you can just choose 2, 3, or 5 to do tests with this method. So we have Alice on the left who chooses some number, lowercase a, and Bob chooses B. And they don't tell each other this number and they don't pass it across the unsecure channel. So now they take G and they use their secret number as an exponent. And then they do a modulo operation on it. So now they get another number, and this being uppercase A and uppercase B. Then they trade these numbers across the unsecured channel, and then they do further math with them with exponents and modulo, and they end up with the same secret number. This happens because of this property where you have a to the b mod p equals b to the a mod p. So they're able to exchange their capital B, capital A, do another operation, and end up with this secret number. Let's take a look at this in practice. We're going to start off with G equals 5 and P is 9521. So Alice chooses 102 as her secret number and computes 8193. Bob starts off with 26 as his secret number and he ends up with 5527. They trade these numbers, do the rest of the calculation, and they both end up with 9187. So now they can use 9187 as their secret key to encrypt messages and send them back and forth. Now, why does this work? Well, suppose Eve is sitting in the middle. What she sees is G and P and capital A and capital B. In order for her to figure out what the secret key is, she would have to figure out what lowercase a and lowercase b are. So this is what she's got to work with. The thing is, there is no mathematical formula for computing A or B. You have to use brute force. It's the only way. So Eve would have to have a tremendous amount of computing power so that she could iterate through every possible A or B and try to figure out what it is. Now, if your numbers are kind of small, like we've been working with 4-digit numbers, yeah, you could write a program that would iterate through these and would figure it out in a short period of time. But what if your P is extremely large, like this big? And what if this is the answer that you got? What's A? Well, I don't know, because my calculator choked when I tried to put this number in. So you can imagine that if you had to compute this for several values, it would take an enormous amount of computing power, more than most hackers have. And that's why the Diffie-Hellman Key Exchange Protocol was considered very secure, especially in the early days of exchanging information across the internet. And it was ingenious in its use of modulo math to compute a secret key that could be used to encrypt a message.